Now, here's the thing. This actually has the equation s times a plus t times b equals the GCD between a and b. It has infinitely many solutions. Okay, infinitely many. How can this have infinitely many? Well, all we're saying is that 13 and negative 31 are kind of the first two values that will do this. I mean, 13 is the smallest possible integer for s that we can have. Now we can certainly make them bigger or invert their signs. Here's how. So let me just point out in our equation 13 times 296 minus 31 times 124. One thing that I could do here, and this equals 4, I'm going to leave myself a little bit of space. And what we're going to do is we're going to perform a little add 0 trick. Okay, so we can probably agree that if I add something and simultaneously subtract it, then those two quantities will cancel out. So let's recall that this value here is a, and this value here is b. Now the trick is to both add a times b and to subtract a times b. This right here still equals 0. I haven't changed the left-hand side of the equation. I don't need to do it to both sides because this just cancels out. But the power in doing this is I'll have 3 times 296 minus 31 times 124 plus a times b. Okay, so plus 296 times 124 minus 296 times 124. And that all equals 4. Again, these two terms still zero out. But if I think about the 296 and 124 as I have 296 124s and I have negative 296 124s, then I can actually appropriately add them as multiples to, I currently have 13 296s here. So if I rewrite 296 times 124 as 124 296s, and I write this as negative 296 124s, like this, then I can see that these are like terms right here. These two are like terms. If I have 124 296s and then 13 more 296s, that gives me 137 296s. And then here I have negative 31 124s. Here I have negative 296 124s. Negative 31 plus negative 296 is going to be, let's see, negative 327. Negative 327 124s. And I'm claiming that this still equals 4. Well, assuming I've combined like terms properly, 137 times 296 minus 327 times 124 indeed gives me 4, and this checks out. So I've just found a new coefficient here and a new coefficient here that will satisfy this equation. So if I look at the possible values for s and t, the ones that I came up with the extended Euclidean algorithm are unique. I'll get 13 and negative 31. But I also came up with another pair here, 137 and negative 327. Now I could do the same thing again. I could again add 124 times 296 and subtract 296 times 124 and adjust these coefficients accordingly to produce another solution. So let me do that. 137 times 296 minus 327 times 124 plus 124 times 296 minus 296 times 124. Again, those are like terms and they add up to 0. So I haven't changed the equation any, but I can do the same thing. Once again, I have 137 296s. I have 124 more. 137 plus 124 gives me 261 296s. And then here I have negative 327 124s. Here I have negative 296 124. So in total I have negative 327 plus negative 296 is negative 623 124s. And I'm claiming that that should still equal 4. Let me check my work. 261 times 296 minus 623 times 124. Lo and behold, I get 4. So let's see if we can generalize our pattern here. So in general, because I know that with numerical values this could get a little trickier to keep track of. Let's say that we found, and I'll up here also populate our new pair, and we can keep doing this indefinitely. If we have S times A plus T times B equals the GCD of A and B, then we said that one thing that we could do to generate another solution is to add A times B and subtract A times B. And that still equals the same quantity, the GCD between A and B, because let's recall that this right here is still equal to 0. Well, not only can I actually add A and B and subtract A and B, but I can do it as many times as I want. So here's what I'm going to do. I'm going to say, well, since I can do that as many times as I want, I don't just necessarily want to keep repeating these steps. I'm going to say that I could actually add K copies of A and B, but then I would have to subtract K copies of A and B. Okay, those still add up to 0, and K is just some integer. It can be any integer. I can do it negative 2 times, 3 times, 4 times, negative 5 times, negative 4 times. Doesn't matter. These two will always cancel out because KAB minus KAB is still 0. So I get to choose that K, and for this example, K was equal to 2 because we added AB and subtracted A and B here, and then we did it again. We did it twice. All right, so this is going to give us a nice general result. So let's write it like this. We have S times A. We're almost at the punchline here. S times A plus T times B plus, and I'm just going to go ahead and write KB A. And over here I'll do minus KAB. So the way I'm going to think about this is I have KB copies of A, and here I have negative KA copies of B. Now again, all I've done is, because multiplication is commutative and associative, these two still cancel out and give me 0. Thus, the left-hand side still adds up to the GCD of A and B. Okay, now let's just combine like terms. Let's switch colors here. So here we have S copies of A. Here we have KB copies of A. So how many total copies of A do we have? Well, we have S plus KB more. So we have S plus KB copies of A. And then here we have T copies of B. Here we have negative KA copies of B. So combining like terms, we have T minus KA copies of B. And And that will still ensure that we get the GCD between A and B. Okay, so what's the takeaway here? So to generate solutions, first find S and T by the extended Euclidean algorithm. So that's just our standard process that, depending on whether you like the forward substitution method here or the back substitution method, like in our last video, you can decide how you want to carry that out. To generate solutions, well, to generate additional solutions, notice that this solution right here really creates the unique solution for k equals 0. Okay, so this is for k equals 0 because you notice if k is 0, then you just get SA plus TB equals the GCD between A and B. And now to generate solutions, pick additional integers k and generate pairs. Okay, let's actually do this. We've already kind of created this ST table, but I'm going to create an KST table. And for our example up here, where we originally had 13a minus 31b equals 4, 13a minus 31b equals 4. Now remember, a and b are just 296 and 124. And this is our value of s. This was our value of t. Now this is when k is equal to 0. By default, you find the s and t for a k of 0, because again, it's just sa plus tb. And now I'll pick another value of k. So if I pick the value of k of 1, well, let's see. The s, this will actually be s plus kb, and this will be t plus k, t minus ka. Okay, that's that and that. So if k is 1, then I'll take s, which is 13, plus 1 times b. b is 124. So if I take 13 plus 1 times 124, I get 137. And if I take t is negative 31, minus 1 times a, which is 296, I get negative 327. Now that's consistent with what we came up here. This was just for one iteration, k equals 1. And I can repeat this indefinitely. I can now do s plus kb, so 13, maybe I'll write that out up here. This is really just 13 plus k times 124. This here is negative 31 minus k times 296. So if I take 13 plus 2 times 124, I get 261. And then if I take negative 31 minus 2 times 296, I get negative 623. And let's just check our work up here. We got 261 and negative 623. Now the beauty of this is I could pick any value of k. There are infinitely many, and remember, k is an integer, so k could actually be negative 1. Okay, if k is negative 1, then I'll have 13 plus negative 1 times 124. That will give me negative 111. And negative 31 minus negative 1 times 296 will give me 265. The reason I plug in a negative here is because in some cases you want the coefficient of, say, a to be positive, like we have for when k is positive, but we have certain circumstances where we might want the coefficient of a to be a negative, and that's going to involve subtracting 1 times the value of b. And so we'll go the opposite direction if we, say, do -1, -2 here, and we could find these values as well. This one will start to become more negative, this one will start to become more positive, because here we're subtracting a negative, we're adding, and here we're adding a negative, which is subtracting. So not only do we have control over those infinitely many solutions, but we can say the solutions are of the form S plus KB. Okay, so for our problem that was S plus KB and T minus KA. Okay, for our particular problem, that equals 13 plus, I'll write it as 124K, and -31 minus 296K. And this is how we would describe the infinitely many solutions where K can be any integer. So, pick additional integers K and generate pairs of the form S plus KB and T minus KA. S, T, A, and B are already given to us, and K we get to choose as a value to generate a brand new set of coefficients.